Thank you for coming to the talk today. Yeah, Cambridge Park as well. We kind of took over the room this morning. Just quickly to do some setup. So a lot of what we're going to do this morning will be in a notebook. So it's great if you have it working. You have two options here. First one is you go to my GitHub and you clone that, and you should have the data. I wrote some functions in the helpers.py because I don't want to have like a lot of messy stuff in the notebook. And you've got all the setup instructions here. So that's the first option. If you can't be bothered setting it up locally, I've tried to do a Google Colab as well. So basically, you click on this thing here, or you copy paste this URL, and that should give you that. So that gives you access to a notebook remotely that you can open in playground mode. And once you do that, they will ask you to log in with your Google account. So if you have a Google account, and then you can actually execute the cells like you would do in a normal notebook. So I'm putting the URL again. Maybe I'll give you 5 minutes so everyone is set up with that. So either GitHub or Colab. I have a short URL as well for GitHub if you don't want to type that. And yeah, if you, so I'm gonna put, yeah, putting that on the side. That's not what I want to zoom in on. What? Okay, cool. Let's get that, and just want to show that as well. Cool. Yeah, so if you're on Colab, you can run the first cell to start with. It's just to set up everything. So I've got to install a few libraries and download some data. So if you just run this one, then you're good to go, and we can move on. Do you need a little bit more time? Maybe who has it working already? Ooh, just one person. Okay, cool. So 2 more minutes maybe. Also, I like to live dangerously, so I actually pushed to the GitHub an hour ago. Just changed the version of SHAP because they've got I've been using an older version, and now they've changed the API, so hopefully everything is going to work. But who knows? Right, so well, at least you have the URL, so I'm just going to get started now. How do I put that back? Yeah, cool. Great. So, so yeah, today we're going to talk about interpretability. That's going to be really fairly introductory. I just want to present a few libraries that you can use to interpret your models. So it's also going to be fairly applied. We'll start with just a really quick introduction on why it's useful, and then present those 3 libraries here. So the first one is Eli5. That allows you to interpret white box models, so models that are not too complex. And then we see Lime and SHAP that are actually allowing you to generate explanations of more complex models. So why do we need and why do we care about interpreting our models? So let's say you've done all the work of a data scientist, you've cleaned, pre-processed messy data. So as we've said, some others have said yesterday, it's most of the job of a data scientist, cleaning messy data. Then you've engineered really fancy new features. You're quite proud of them. You selected the best models. You've tuned it. You've trained it. You got great performance. You're really happy with what you've done. But then your boss comes to you and is asking, well, can you explain how your model works and why does it take those decisions? And that's something that is more and more happening. Machine learning is used in more and more industries. Everyone wants to be on board, start building fancy models. You'll see them in all industries, insurance, banks, even the police is looking at trying to predict if someone is going to commit a crime in advance. You don't want your model to be a black box in those situations. You don't want it to pick some, like, for example, having gender bias or bias towards some minorities or things like that. Here I've added another example, social media. I think it might seem less important than the three above it, but I think it's super important. If the example I wanted to bring here is, say you have a company doing online, like a casino or poker or whatever, and they want to target ads on social media. If you have a model that is telling them, well, the best person to recommend going on your website to do gambling is people that have gambling addictions, then it can be a really big issue. So that can have a really bad impact as well if you don't have any control on what your model does and what it picks up on. So black box models, it's not really an option in many industries. So I want to just go through two examples. The first one is really bad. The second one is just inconvenient. So the first one, I have a quote from Katie O'Neill here as well. So models are opinions embedded in mathematics. So that's the whole garbage in, garbage out thing. If your data has bias in it, your model is just going to learn this bias, and then you can't say that your model is fair because it has just learned whatever you had in your data. So an example here, and I think that's a real example she gives in her book, that say you work at a big company, you want to predict performance of your employees. As data variable, you have past performance reviews for individual employees for the last 10 years. But what if your company tends to promote men more than women? Then those performance reviews will be more positive for men than women. And your model is just going to learn that. It's just going to do, if the employee is a man, then they're more performant. And that you will just embed that bias into your model. And then when you're using it, you're just going to enforce that. So that's something really bad. And that's something you need to spot early before deploying your model, or you can just embed that in all your well, whatever you're doing with your model later. Another example is just sometimes you'll be building a model that is actually not doing at all what you expect it to do, and that's an example that they that they quote in the paper "Why Should I Trust You?" So that's the paper that came when they released the library Lime that we're going to talk about later. So they wanted to classify images, some of wolves, some of huskies, and they ended up having good accuracy. But what they figured out when they started using Lime, and that's something we're going to show later, is that the model wasn't actually looking at the at the dog or at the wolf, but it was looking at the background and just saying, if there is snow, just classify it as a wolf. If there is not snow, classify it as a husky. So what you've done, you thought you had a nice classifier wolf versus dog, but actually you just built a snow detector. So that's something, again, that you want to spot, and for that you need to be able to analyze your model and see what features it picks and everything. So that's what we're going to do today. Now there are different types of models. Some of them are actually really easy to interpret. So that's the case of linear model, for example, logistic regression. Here you have a weight associated to each feature. You know the exact contribution of each of the features. You know if it's negative or positive. So I give a really basic example here. When you're increasing x1 by 1 unit, you know that your y will increase by 3 units. So you can explain exactly what your model does and how it takes its decision. A single decision tree is really easy to interpret as well. You've got the whole decision path. So when you're making a new prediction, for example, here, that's from the Titanic data set, I think. So you're looking first, is it a male? Well, if it's a male here, you're in trouble. And you're much more likely to die. So that's, again, you can explain exactly how the decision was made. Now you have other models that are a little bit harder to interpret, and that's a good example is ensemble models. So they still, I mean, random forest, for example, or gradient boosting, they will still rely on trees, so you can still get the feature importance. But first thing, the feature importance is calculated differently in different libraries that you'll be using. In random forest, it will aggregate, it will average all the feature importance from all the trees that you have in your model. For boosting, it's more tricky. Every library will have a different definition of how, when you have feature importance from all your trees, how do you aggregate that? So you can't always really trust it, and you don't have a unified way to know what's the importance of feature. And also something that it doesn't give you, it's telling you how, you know that a feature is important, but you don't know how, if it's positively affecting your decision or negatively. So that's something that you'd like to know as well. And then you have another category of model that is completely a black box that you can't really do much with it, and those ones are probably the hardest. So then there is a fair question that you can ask. Does it mean that we have to use only a simple model? Well, that could be a solution. That's probably the best solution. Like if you're using, and that's, I think, what Hugo was saying yesterday, that a lot of the data scientists he interviewed in his podcast were saying that logistic regression is really underrated. Like, if you want to interpret interpretable model, the best way is to use a really simple model that you can interpret easily. But that's not what I'm here to talk about. So I'm here to talk about the second option. What if you still want to use fancy models that are more performant, but still be able to interpret them? So there you have a set of techniques, and that's what we're going to talk about right now. So just to start with, Eli5. So I don't know if you're familiar with the Eli5 subreddit, but it's explained like I'm 5. So it's here they created a library that is just looking at the different internals of scikit-learn models. So it works mostly for simple models. So the first category that I was showing there, logistic regression, single decision tree, and it's explaining really simply what is important and by how much. So linking your weights to features and things like that. So we'll show that in a notebook in a second. It provides a global interpretation. So it tells you how overall your model works. But it can also be used to provide a local explanation. So for a given prediction that your model has made, how did it take its decision? Just quickly on the API, so you've got a few, and here we'll see only 2 of the methods in Eli5. The first one is show weight, so it's to have the global interpretation of the model. And then you can explain a single observation with show prediction. So let's go to the notebook. Do you all have it working now, at least with Colab, if not locally? Yeah? Who still need more time or setup or has issues or whatever? Cool. Great. That's amazing. Yeah, I can put it back. Where is it? Disappeared. This one? Yeah, I'm just going to copy it in the notebook so I can start working as well. Oh yeah, also something, I've got a comment here. I'm going to use features from Python 3.6 and some new classes that were introduced in scikit-learn 0.20, so that's the latest version. So if you're using older versions of scikit-learn, just make sure you upgrade before, otherwise you won't be able to run it. Right, so I'm importing a bunch of things here, just quickly to, well, pandas obviously, then a few pre-processing classes from scikit-learn, so one hot encoder because they've got categorical values. The column transformer, so that's the one I was talking about. That's from the new version of scikit-learn. I don't know, who here has used the column transformer before? No one? Oh, yeah, great. Do you like it? Yeah, it makes the pipeline like much cleaner. And then the pipeline and a few classes to compute accuracy, classification report, and train test split. And then here I'm gonna end up with, for the whole workshop, we're gonna focus on 4 models of increasingly complex. So we'll start with logistic regression, which should be really easy to explain. Decision tree classifier a little bit harder. Random forest classifier a little bit harder, but still possible. And then the gradient boosting, where the different trees don't carry much meaning, so it's harder to interpret. So let's load all that. Just a quick introduction of what's dataset. So I just find it on UCI website that you can access it here. And it's basically related to a direct marketing campaign. So a Portuguese bank just contacted some of the clients, and they try to have them subscribe to some term deposit. So that's why we're going to predict whether the client subscribed to it or not. And that's going to be the variable y. So let's load that. Here we notice that there is imbalance of the classes. So only a few amount of people actually subscribe to their term deposit after the marketing campaign. So we'll need to keep that in mind. Thankfully, all the models we're using easily support class imbalance, and we can add more weight on the minority class. So we're going to build x and y. So y here, we're just mapping no to 0, yes to 1. So every time you see a 1, that means the person subscribed. And yeah, we're ready to hear a few introduction on what the features are. So we've got the age of the client, we've got their job, marital status, education, a bunch of things. We've got a month when the campaign happened, the day of the week, all sort of things. We've got some weird features that I investigated a little bit. It seems to be related to the state of the bank. So I don't know why they included, for example, the number of employees in the bank when they contacted the clients. But that's there. And spoiler alert, it's actually one of the main features. So and we'll talk a little bit about why later. Now, yeah, there's just quick notes. Duration here, it's a big data leakage. That's the duration of the last call, so that's when they were supposed to actually subscribe to the plan. So here we're gonna get rid of it, because that's if that last call to subscribe to the plan has a duration of 0, that means they didn't subscribe to the plan. If the duration positive, that means they might have subscribed. So we're just getting rid of it. And yeah, we'll go from there. Then a few values here, categorical. So what I'm doing is just defining a list of numerical features, categorical features, and I'm going to process them differently with the column transformer. So here, if you haven't used the column transformer before, what you've got to do is just define a transformation that you want to do on each group of features that you have. So here, I'm saying that for my numerical features, I'm just keeping them like they are. I don't modify them whatsoever, just keep them as they were initially. But for my categorical features, I'm going to apply the one-hot encoder transformation on it. So that's my preprocessor object that I can then later on use in a scikit-learn pipeline. Has everyone used scikit-learn pipeline here? Yeah, cool. So we're going to do that. Now we have our preprocessor. We can define our 4 models. So the first model of logistic regression is just my preprocessor and the logistic regression algorithm. Here you see I've defined the class weight as being balanced. I'm doing the same thing for decision tree. So I have got my decision tree model that has a preprocessor decision tree algorithm. Same thing, class weight balanced, random forest, and then the XGBoost model. XGBoost, notice that it's not actually from scikit-learn, but it comes with the scikit-learn API, so I can just use it in my pipeline as any other model. Right, so now we're ready to go. Obviously, we split the data into train and test, so we can actually check the accuracy of our model. Here you notice the arguments stratify, just so we make sure that the distribution of y's is the same in the training set and testing set. All right, so we're good to go. So now we'll look at Eli5. So with Eli5, we only look at the white box models here. So the logistic regression and the decision tree. We are not going to use it for the more complex models. They actually have functions that should give you interpretation of them, but we'll prefer Lime and SHAP for that. Right, so logistic regression first, and that's where it might take a while. I just wanted to do the whole process here live, but that means I'm doing a grid search CV live, which might take a while, but here it was really quick. So I've got my best parameters, best score. I'm overriding the parameters of my model to be the best parameters, and here and I can verify that it all worked well. So here my best C after grid search was 1.5. If I just check it here, this should be a 1.5 somewhere. Yeah, here it is. So I've probably overwritten into my pipeline the value of C. So now I can fit it on my training set, and I'm good to go. Well, the first thing you do then, you've got your model that has been tuned. You can now test how accurate it is on the testing set. So here, 83%. Let's look at the actual classification report. Yeah, and as usual, we're actually not as good as the accuracy score would, as you would think, looking at the accuracy score only, because the class 1, which is the minority class, you've got a much lower recall and precision. So that's something that you can do first, but then, I mean, here there isn't much more we can do. We'll look at Eli5 to interpret your model. So we know the overall accuracy. We know that it's good enough to predict the majority class 0, but to predict the minority class 1, it's not that good. That's the first thing you know by looking at the classification report. The second thing is that we want to know how different features are picked in our model. So Eli5 allows you to do that. We're just importing it here, and we use the show weight method that will just look at the weight. It's not doing anything fancy here. It's just looking at the weight of your logistic regression and showing it with nice colors. It's nothing crazy. I'm passing my model, so I need to take it into my pipeline because it needs to get the logistic regression object. So that's why I'm using this name step model here. And you can see my features and the weight associated to it. Here it's not amazing because the features are just numbers, right? So we'll want to pass the names of the features here. So there is a little bit of gymnastic to do because the features have been generated through after one hot encoding. So I need to actually get not the original names of the features, but post one hot encoding. So am I good with time? Yeah, so probably gonna go really quickly with that because the code is not that important, but I'm basically getting my preprocessor. Then from the preprocessor, I can get my preprocessor that preprocesses the categorical features, which is the one-hot encoder. And from the one-hot encoder, I can get the list of one-hot encoded categories. And if we just look into this object, it's basically telling me for each feature for which I've built one-hot encoded new features, all the possible options. So here, that's the first one is the job, for example. So I've got the list of all possible jobs. So once I have that, it's fairly easy to build a list of features. I just need to flatten it. Oh, and here you see that I'm using a f string. I'm quite happy with that. And if I look at that, that's basically the object I've built, right? So that's the list. There's the flattened list of all my features post one-hot encoded, and encoding with first element is the original feature that was there. So for example, the job, and then the value it took, right? So that should map exactly with all the dummies I've created. Then I just add that up to my numerical features, and that's the list of all my features in the dataset. So I can check that here, but if I just, for sanity check, if I just build a new data frame that has the data post-processing and those columns there, I see that I have the right name. So I can trust this little gymnastic. Right, cool. So now that we have the name of all the features, we are able to make Eli5 a little bit better and see what features it's actually picking. And now it seems that the most important feature for that logistic regression is whether the campaign happened in March, which might be weird. I don't know. That's the first thing you can do. Once you have this information, you're able to talk to whoever was in charge of the marketing campaign, ask, was there something you did differently in March? So you're able to communicate this information better. And that's what Eli5 and all the libraries we're doing today is supposed to help with. It won't give you the answers to all the questions. It will just give you a way to communicate that and discuss with whoever knows more than you in the domain, or if you know a lot in the domain, you can answer those questions yourself. So here it's telling you, it's picking principally whether or not the month was March. Great. So now we can use the second function that we saw from Eli5, which is show observation. So it will it can explain a single prediction. So here, let's pick this person, so 27 years old. We don't know their job. We know that they're single, that they've got a university degree, so quite a bit of information. And that person happened to subscribe to our marketing campaign. So now we'll use Eli5 to see how our logistic regression decided whether or not that person subscribed. So if we just run this, and here I've done exactly the same thing. I've used the show prediction method, but I've passed my model. I've passed the data set. I need to transform it with the preprocessor first, just to make sure it has access to the dummy variables that I've done. And then the list of all my features. So if I do that, here I see what it looked at, like what it looked at. So it actually predicted that this client subscribed to the term deposit with a probability of 0.96%, of 96%. And it principally looked at this variable, which I'll need to look it up here. The consumer price index. And actually, that's an interesting one, because that's one of those features that I find weird that are not actually linked to the client, but that are linked to the company. So here, that's the first thing you can say. It's trying to use as a proxy whatever your company was up to at that time, right? So here you've got that's monthly indicator that they compute at the bank, and that's what it's using to make their prediction whether or not someone will subscribe. So it's actually not even looking at what the client has as characteristics, but only saying that this index here has these values that's used as a proxy to know where, like, around what time you did the marketing campaign, and that's how it makes its prediction. So by using that, you can already tell that your model is probably not that great, because it's not really good at predicting based on the attributes of the person. It's good at predicting based on what marketing campaign it was, or something like that. And also, like, it's got a really big negative weight on the number of employees, which, same thing, is just an indicator related to the bank at that time. Right, so we can use Eli5 for decision trees as well, so we'll do it right now. I've got to tune my model first. I'm going to do the same steps as I did before.
That last example?
Yeah.
Sorry, just one quick question.
This one?
Is it possible? Yeah, so we've seen how big of an influence these factors have, and we see here the value of this feature.
Yeah.
Do we see kind of potentially what the coefficients are for this regression somewhere, or?
So that's a good question. So here you've got the coefficients. Okay. So the coefficients are in your global explanation of the model. So when you're using show weights, that's what it's telling you. When you're checking the local explanation, so for a specific prediction, what it's doing is just multiplying whatever value that that observation has with the weight. So here, what you see, the number here, it's really big because the value for that specific prediction happened to be that, and it's multiplied by whatever weight your logistic regression has. And same thing for the number of employees here.
Yeah.
Yeah.
It'd be nice to print that here on the same table, so it's clear.
Do you have the weights as well?
Yeah.
There might be a way. Show, I don't know. Just
no problem.
Documentation. Right, so we can do the same thing for a decision tree. Oh no, I'm doing the grid search again. Oh, I can kill it. Perfect, because I've done it already. So I know my best parameters. Setting that again, that's getting a little bit boring. And I get the accuracy score is a little bit better than before, I think. Still get the same classification report, so I still don't have a great model, but that does the job. And here I can do the same thing. So I can use Eli5. So, and that's one of the advantages of Eli5 is that, because you could just tell me now that, oh, well, getting the weights for my logistic regression, I can do it by just doing dot weight on my logistic regression. And you could do the feature importance from the tree as well. What Eli5 provides you, well, it's got nice colors, it's the first one. But it also provides you a unified API to do that. Right? So whether you have a logistic regression, decision tree, or other models, you'll be able to use this show weights. So you can compare models really easily because you've got a proper API to do that. So let's look at the decision tree here. Same thing, it's picking on the number of employees. So even the decision tree is a pretty bad model as well. And here it shows the decision tree if you want to look into more detail. I've got no idea how well I'm doing with time. Is it finished at midday? Yeah? Quarter past, okay, cool. Plenty of time. Right, and you can also use the local interpreter. to see for specific observation. So here we're going to look at the same observation. You see that it will always have the bias first, so it's just where it starts. So at the top of the tree, it already has an assumption of the probability. So here we start with like 0.5 chance of being class 1, and then we check the impact of each feature from there. So you will always have the bias first, and then you look at the features after that. So the most important, again, even for this specific prediction, was the number of employees. So your model isn't great. Yeah, that's all for Eli5. Do you guys have any questions for Eli5? Maybe it's good to do it now before we start using other libraries. No questions? Great. So let's go back to the slides and talk about Lime. Okay. Right, so Lime. So here we've used Eli5 to interpret simple models, and that gives you that unified API to show you what features are important, and also to do local interpretation of your models. What if your model is more complicated? So that's the problem that Lime is trying to solve. So they released a paper in 2016, Why Should I Trust You? That is explaining their approach to that. And so I'm going to explain how it works in a second. Just two things to keep in mind. It's local, so it doesn't do a global interpretation of your model. You can't use that to know how your model works globally, but only you can see how it made its decision for a specific observation. It's also model agnostic, so you can use it on any model of whatever complexity you want. So you can use it on the simple models you've seen, but also on the more complex models that we will do later. So what it does is that given a model and given a specific observation, so here we have a patient, for example, with some symptoms, your explainer will tell you what symptoms your model picked in the data, and that's something, again, that you can then communicate to the domain expert, so here, the doctor. So that empowers you understanding better your model and talk with the people that know the field. So how does it work? So that's a drawing that they have in their paper. That's that gives a good intuition of how Lime works, but it's not exactly how it's implemented. So we'll just to explain this one, here you have a really complex model that is not linear at all. So that's what you see in the background. So you have two classes, the blue and the is that orange or pink, and you build a model that is really not linear. That is telling you whether something belongs to the class blue or the class pink. So what Lime does, it's trying to for a given observation. So here we want to say wherever the cross is here, we want to generate an explanation of this decision. So what Lime will do is trying to approximate your model with a linear model in this area, and then use the weights of that linear model as interpretation, as we've done before with Eli5, for example. So the way it does that is by sampling some data randomly around your observation. So you say, explain this red cross here. It will generate some data by sampling from the distribution of your original data, and then it will fit a linear regression in the locality here, and use the weights of that linear regression as an explanation. So that's the intuition. It's actually not exactly how it works, because things aren't binary, they are probabilistic. So, and it's much harder to explain in 2 dimensions, so I'm moving to 1 dimension here. Say you have a model that wants to, that predict whether or not someone is likely to have a cancer based on some features. Here, I'll just have age as a feature. So say you have you have one patient that is 20 years old, and your model predicted some probability here, and you want to explain that. So what Lime will do is first sampling from the distribution and predicts all those values. So here it sampled a lot of data around that 20 years old spot, and it uses your model to predict the probability based on that. And once it's done that, it's able to fit a linear regression. So here we're not in the binary case anymore. We have probabilities and we fit a linear regression in that. So here, once it's done that, it can tell that around 20 years old, adding 1 year doesn't seem to have much impact on the probability. Whereas, say, if you have another patient that is older, you have the probability here. You're sampling from the distribution, generating some probabilities. You fit your linear model, and here, by looking at the weights associated to your linear regression, you can tell that around this age, the age actually has more importance, and the weight associated to that feature age is much bigger. So that's how you would be able to generate observations, to generate explanations. Yeah.
What distribution are they sampling from in the background?
So you need to pass your data to the Lime explainer.
Sampling the data
Yeah.
from the underlying explainer?
Yeah. So for numerical values, it's just getting the distribution. For categorical values, it's looking at the frequency, and so it's picking from there. Right. So so I explained. You choose an observation. You create a new data set around it. You calculate the distance between the points. So that's something I didn't mention here because it was hard to visualize, but it's assigning different weights on the points that you're generating, just to know how similar they are to your original point that you want to explain. So you don't want a point that is quite far off to be weighted the same as things that are really similar to to your point that you want to explain. And then you use your model to predict classes. Here also something that I omitted. Lime is one of the parameters that you pass to Lime is the number of features you want to use for your explanation. So here we only have one feature, but if you have multiple dimensions, you can say generate an explanation with 3 features only, or 4 features. And then it fits a linear model, and it gives you the explanation based on the on the weights. It can work with images as well, and that's a really cool thing that we might do if we have time at the end of this of the notebook. But given an image, it can also tell you which part of the image it used to predict. So here, it predicted frog with a probability of 0.54, and it tells you that the main thing it looked at to say that it's a frog is the head here. It also predicted it could be bulls with 0.07 probability, and it looked at the eyes and the fingers of the frog. It also predicted other classes, and it shows you in the image what so that can be a really nice way to spot if your model is actually doing the right thing, and that's how they did the first example that I showed at the beginning. Right, some drawbacks before we go to the notebook. So it can be unstable because it depends on the first random sampling that you're doing. Whatever model you're going to build and explanation that you're going to show depends on that initial sampling. It's also fitting a linear model. So if your model isn't locally approximable, can be locally approximated by a linear model. So if your model is really nonlinear, then your linear regression fit is not going to be good. So your explanation won't be good either. Lime gives you access to the R-squared, so you can actually see if your linear regression locally was good or not. And it can be fairly slow for images in particular because it needs to generate this data set. So for images, it's even harder. It needs to generate tons of images from scratch before generating an explanation. They have implemented various explainers, so you can work with tabular data, and that's what we're going to do, keeping the same example, but you can use it for time series, for images, and for text as well. So if you're working with those type of data, I encourage you to take a look at that. Just a quick word on the API. So you're generating first an explainer that's where it will learn the underlying distribution, and they will know how to generate a data set and everything. Once you have your explainer, you can call the method explain instance on it, so passing a given observation and your your prediction function from your model. Try to explain how your model works by fitting the linear regression, and then you have, once you've generated an explanation, you can visualize it in different ways. So let's do that. Right, so here we want to make it a little bit more complicated, so we're going to use to fit a random forest and XGBoost model first and try to interpret those. So again, I was a bit ambitious and tried to do grid search live. So it's taking a while. Probably it's faster if you guys are using Colab. It's actually probably faster than my laptop, maybe, because Google Cloud. Great. So accuracy a little bit better than before. Classification report. Here, just wanted to prove that I wasn't lying, and Eli5 can actually work with ensemble models. So here was my random forest. Yeah, it's interesting. It gives you pretty much the same results as before. It adds the standard deviation, because you've got multiple trees in your ensemble now, so you can know how confident all your trees are in picking this feature as more important than the others. And let's do the same for gradient boosting. Please. Cool. Accuracy, woo, really good. Oh, but here my recall is really bad. I'm having a really bad coverage of the class one. Anyway, that's fine. So let's import from Lime the tabular explainer. So that's the main one we're going to use here for tabular data. We need to create that explainer that I was talking about. It's actually more complicated than just passing the data set, because we're working with categorical variables. So it has the whole one-hot encoding issue. The problem is that the explainer from Lime needs the categorical data not to be dummies, and also not to be strings either. So they need to be integer labels, but still with the original features. So that means that we've got to do a little bit of gymnastics again to get the data set in the right format, but still be able to use our model. So probably going to skip the details of that. You have the code available on how I managed to put things together so it's in the right format for Lime. But one thing that we need to do first is provide the list of all categorical values, categorical features, and their possible outcomes. So Lime can learn from that. So I'm generating it with this little code snippet here, and what I'm doing is just basically saying that feature index 1, which is the job, has all those possible values. Feature index 2, all those possible values, and I will need to pass that to Lime. Here, I didn't even want to put that function in the notebook, so I created a helpers file. And what it's doing, it's just something super basic. It's just taking a data set, and it's looking at all the categorical values in the data set and converting the strings to integer labels. So I didn't want to have it here to confuse people. So if you want, you can see on my GitHub, it's right here. But yeah, so I'm going to import that. And we can see that it works. So if I give xtrain to it with a list of categorical names, it's properly. So if I check xtrain first, so xtrain is in the right format for my model. So meaning like the original data set. And then when I use the convert to Lime format, it's just applying that transformation to change categorical values into integer labels. So once I have all that, I'm able to create a Lime explainer. So I need to pass all those things. So the first one, my data set that I've converted to the Lime format. I need to specify that I'm working with classification. I need to give a list of all my features, so it's able to provide me with a nice explanation that tells me the name of the feature, not just the index. I need to pass the name of the categorical values, so it knows which one to treat as categorical, and then as I was saying earlier, it will need to not it will need to look at the frequency when it's trying to sample from the distribution. And that categorical names dictionary that I've created above, saying all the possible values. So that's a little bit of wiring here. I think it's not worth explaining that more. You'll probably need to Google it if you want to use it for the first time anyway. So no point spending too much time on that. And once I have my explainer, I'm ready to explain stuff. Amazing. So let's pick an observation again. Define I equal 2. So that's one of the clients, 35 years old, technician, single, professional course. They contacted them with telephone. Great, good stuff. Now I can see how all my models generated prediction for that specific client. So the true label was 0. That person didn't subscribe to our term deposit. The logistic regression here predicted class 0 with 71%, decision tree with 75%, random forests 80%, and XGBoost 92%. So actually, here my XGBoost seems to be the most confident in predicting that this person won't subscribe. So, all right, seems fine. Now again, need to convert that to Lime format. So that's a bit annoying, but fortunately I have a fancy function to do that. So let's do that. And now we ready to generate explanation. Well, actually not really. There is something else. Because here, if you go back to where I presented the API, to generate an explanation object, we need to pass an observation. We have that. Well, we need to have an explainer first. We have that. We need to pass an observation. We have that. But we don't have the predict function. So if your model would be really basic, the predict function would be just the .predict from whatever model you've built. But here our model has one hot encoded features. So our predict functions need to be able to work with the Lime format. So it needs to, when Lime is going to use our model to generate predictions, probabilities, it needs to be able to pass that data set in the weird format with the integer labels and generate probabilities with our model. So that means we need to override that a little bit. So I've created another function here that is just taking whatever data Lime wants to use. I'm having this invert parameter here, so that will just convert it back to the right format for my model, and then I'm calling my model. Right? So it's just a wrapper that I've done so that I can pass from the Lime format back to the original format and call my my predict proba. So once I have that, I'm able to create predict proba functions for all my models. So I have my logistic regression, decision tree, random forest, XGBoost. So all those functions here that I've created with partial are able to predict probabilities using data from in the Lime format. So I can pass those to Lime. Right, so once I've done all this ugly wiring, I'm able to explain an instance. So I'm passing my observation here. I'm going to start with my logistic regression, and I'm saying generate an explanation with 5 features only. Right. So I do that, it's done, it was really quick, and now I'm able to actually visualize it. So I can call show in notebook on my explanation. They have different methods that allow you to do it more programmatically. So if you have a script or something, you can generate an HTML version or whatever. But here we're in a notebook, so we show in the notebook, and that's how it looks like. So it says here I've got the outcome of the prediction. So it predicted 71% to class 0, so the person doesn't subscribe, and the remaining 29% for the class 1. And here it explains what it looked at. So I've got class 0 on the left, class 1 on the right. So I see how each of the features influence the prediction one way or the other. So here I can see that the number of employees, for example, influenced a lot the model into choosing the class 0, whereas other features like those two here influence the model in choosing the class 1. So overall, I still predicted class 0, but I know how all the features influence in one direction or the other. So that's one thing that you can start using to debug your model. So you know if you can then talk with a domain expert and ask, like, is it normal that this given feature here that has a weird name actually influence my model into trying to predict the class 1? So that's the kind of discussion you can start having with domain experts or like whoever did that marketing campaign. And then you have the same thing but presented as core here in this table. You can save that, as I said earlier, in an HTML file as well, which is useful to communicate. So you could just do that and then so I have it here somewhere. Yeah, and just share that with. Yeah, so you could just send this file to someone and share your results. And as I said in the slides earlier, you can also look a little bit into that linear regression that that Lime did for your explanation, and see the R squared. So here we see, well, you can see the different weights, and you can see the R squared at the bottom. So here we have 0.37. So that's not great, but actually, at least with all the explanations I've generated with Lime so far, it was always fairly low. So don't expect it to be really high. It's just like this. But you know how much you can trust your explanation. So that's a nice thing. And here I'm going to do the same thing with all my models. So here let's generate an explanation for the same observation, but looking at my decision tree instead. And here we are. So here R squared is even lower. So the model had a hard time. Lime had a hard time trying to approximate my model locally with only 5 features. Yeah, with a linear regression. But I can look at the at the explanation here. So 0.76% class 0, and here we see like all the features that contributed to this decision. I can do the same for all my models. So that's something that's quite nice as well. It provides that unified API, and you can compare your models and see how different models pick different features in your data. Here they seem to be all focusing a lot on the number of employees, so I think you should really get rid of this feature. Here, number of employees. Oh, here I actually looked at whether the person was contacted with a telephone. So that one is interesting. So finally, your model is doing something right. Hopefully, so you could report that to the people doing the campaign, saying that, well, for this person, that's what seemed to have impacted at least the decision of your model, that you contacted them with a telephone. And then where is my XGBoost? Here it is. XGBoost, So really confident that it's going to be class 0. And again, it's focusing a lot on the number of employees, but then it's also looking at things like whether the person was contacted with telephone. And finally, it's also looking at the characteristics of the person, which is what you'd like ideally. So here, professional training. Right, so that's it for Lime. And now, the last libraries that I wanted to talk about is SHAP. So let's do that. So what is SHAP? So it also originated from a paper where part of the paper is explaining that actually. That's so weird. Okay, a part of the paper is actually explaining that generating explanations for a model consists in can be seen as this framework. So you have your data, you have a really complex model, and that generates prediction. And then in parallel to that, you have an explainer, which is another machine learning model, but simpler to interpret. And that's supposed to approximate your complex model, at least locally, and then you generate explanation from that. So just saying everything that what people did before to explain models is basically this framework. You're saying my model is too complex, I can't look at it, so I'm building another model that is simpler and easier to interpret and locally good approximation of that model, and that's what you use to generate explanations. Then why does it disappear? Okay, cool. Then what they said is that there is a specific type of explanation. It's called additive feature attribution methods, which Lime belongs to this framework as well, which is basically trying to build a local model that is just a linear combination of your original features with whatever value you want here. So Lime is doing it by fitting a linear regression. SHAP is doing it by I've got a weird transitions here. SHAP is doing it by leveraging Shapley values from, which is a method from game theory, and what it's doing is trying to see how a feature is impacting a decision when it's added to a subset. So it's looking for a given feature, say xi. It's going to look at all the subsets of features that do not have xi in it, and it's going to look at the difference when you're adding xi back to that subset. And when it's averaging all those impacts of adding xi to all the possible subsets of features, it's able to tell you how important xi is. So it's doing that for all the features, and that's how it's computing the phi here. So the weight on the different features. Sorry, I'm just fighting a little bit with my transitions. And yeah, that can be computationally expensive because you need to look at all the different subsets of features that are possible and add every time xi and then generate predictions on that and see how that impacted the prediction. So SHAP is providing different optimizations that are model-based. So they have an model agnostic version as well, but they will have different implementation of the algorithms for decision trees, for example, or like tree-based models, and that's what we're going to use in the notebook. So here you have two examples: the tree explainer that is working for all tree-based models that have a scikit-learn API. So scikit-learn, XGBoost, LightGBM, CatBoost works as well. And then the kernel explainer is the model agnostic one. So if none of the explainers work, you can use this one, but it's going to be fairly slow. Right, so the API, quickly, a bit similar, sorry. It's quite similar to Lime. So you first create your explainer from your model, then you need to compute those SHAP values. So Shapley values are those that I was talking about earlier, so the impact of each feature on your predictions. So they compute all the Shapley values at once. So you need to provide all your observations, and then you will compute a big matrix of values that contains the impact of and the importance of each feature. And once you have those values, so that's probably the step 2 is probably the one that will take the longest. once you have that, you can generate explanations for given, well, either locally for given predictions, or globally as well for like how your model works as a whole. Right, so let's do that in the notebook. So we import SHAP. Here we've got to initialize JavaScript as well, because it's got a lot of fancy interactivity things. So let's do that. We create our explainer passing our model. So here, SHAP doesn't have a specific way of handling categorical data, so we don't have this annoying thing to do like we had with Lime. Then I'm getting my observations. Here you see that I actually chose to only calculate SHAP values for 1,000 samples in my data set, because that can be fairly slow and I just don't have that much time now. So I'm generating observations by using my preprocessor on 1,000 random samples in my data set. And then I use that explainer to compute the Shapley values, and I'm saving it as a matrix. That was fairly quick. I think actually the version on Colab seems to do that really well and really quickly, so you can try with the whole data set if you want. Worst case is just the Google Cloud instance is going to freeze or something, so that's fine. Right, so now we can generate some interesting plots from that. So say I want to look at a specific observation here, so I equals 0, so that's the first observation in my data set. So I'm passing the expected value, so that's the Shapley value for, that's the base Shapley value. So that's if my sample didn't lean towards right or left, that's what it would be on average. So here, that's the base value that you see here. And then what it's doing is that it's telling me how different features influence my decision, either on the right, on the left, or on the right, out of this base value. So here, for example, the number, I start from the base value. The number of employees is pushing my decisions towards the class 0. So that's a bit similar to what we've seen before from Lime, right? So it has a fairly big impact, and you can see here in pushing my decisions towards the class 0, whereas all those features here seems to be pushing it on the other side. So we've got that feature here that I don't know what it corresponds to, I think some index as well, whether the person was contacted from a cell phone, and then all the other features here. So that's a nice way to visualize how you're impacted. And by the way, if the so this axis here are the Shapley values. So if the Shapley values are negative, we're going to predict 0. If the Shapley values are positive, we're going to predict 1. So here, all those features on the right-hand side here in blue are pushing my decisions negatively, so towards the class 0. And in the end, I'm predicting class 0. So that's a nice thing that you can visualize for a specific observation. But then the power of SHAP, it allows to do to visualize those things for all the features at once. So here, for example, I've got all my observations, and I can see how that idea of pushing the decision towards the class 0, class 1 can be seen on the whole data set. So I see, oops, you can over here and see that for all those observations here, the number of employees, so that's kind of starting to give you a global understanding of your model. For all those observations here, the number of employees seem to be the biggest, have the biggest impact on the decision taken by your model. And you know also that it was, that the impact was to push it towards the class 0, so not subscribed. So for all those people here, and then for another another group of samples of clients, you can see that this Euribor3M feature made your model predict the class 1. So that gives you an idea of how your model works in general with all the samples that you've provided. A nice thing that you can do as well is look at a feature in particular. So if I want to see how the number of employees influence my decisions for all the samples I've provided, I see it here, and that's, I think, really nice, right? So for the number of employees from like 4,900 up to 5,000, I see that in fact it affected decision towards the class 1, so it pushed it to 1, and then it started to influence it on the other side when it became bigger. So that's actually like the first thing you can start looking at to debug that, and you see that that doesn't seem right? That feels like that's that notion of proxy that I was talking about earlier. Here it seems to be like if the value is between those two, that range, so that's probably at one given point in time, then your campaign was successful, and at another point in time it was not successful. So you can like do all sort of things like that, looking at features, in particular the impact of age, for example. So I see that for this, like from 20 years old to 60 years old, age doesn't seem to have a big impact on whether or not the people will subscribe, whereas up to 60 years old, it has a really big impact in pushing in pushing decision to the class 1, which is subscribe. So you can make all sort of analysis like this on a global level, which I think is really nice and much easier to communicate than a specific observation. And you can also change the axis here, and I'm going to do this one. Well, not the age then. Right, so you can also see the distribution of the number of employees here. So let's just skip that because I don't think I have much time left. Another nice thing that SHAP can do is, so we saw initially local explanation for one single sample, then we saw a more global one that is showing a bunch of local observations together. So that's the one we were doing here. And then you also have a proper global explanation of your model. So it gives you all the different aspects. So here I can see, so if the value is going to red, that means it's higher. So a higher value of the number of employees in red here is affecting my model at a global scale towards the class 0, so more negative. Whereas when the number of employees is in blue, so when it's going down, it's affecting my model globally towards the class 1. So you can see that for all the features, and that gives you also the order in which the order of importance. So you start with the number of employees. That's the most important one globally. So that's what we've spotted already by looking at the different other methods. And then the second most important one is this one. Same thing, the highest it is, so when it's red, it's actually pushing your decisions towards the class 0. When it's blue, it's pushing your decision towards the class 1. And you can see all your features like this. So that's also a nice visualization that you can plot. And another one is the dependence plot. So you can see how features, you can plot two features at once and see how they together influence the decision. So you've got on the y-axis here the SHAP value. So if it's positive, you're going to predict 1, so that the person subscribed. Otherwise, you're going to predict that the person didn't subscribe. So here, the number of employees. You see that when the number of employees is higher, you tend to you tend to predict every time that your model is going, that the person is not going to subscribe, whereas when the number of employees is lower, you tend to predict that the person is going to subscribe. And you can see how another feature here, the contact telephone. So whether the person was contacted by telephone has changing that as well by looking at whether the points are red or blue. Yeah, so that's it for SHAP. Now I just wanted to finish it at quarter past, right? Yeah. Okay, cool. Perfect, really good time now. So I just wanted to show you how you can use Lime for non-tabular data. So there are plenty of examples available online for text data. So you can use those tutorials pretty much out of the box. Just wanted to show you with pictures because I think it's quite nice result. So let's load a model pre-trained from Keras because I'm not that crazy. I'm not gonna train a model now live, a deep learning model live. So I'm just importing the Inception v3 model that is pre-trained on image classification from ImageNet. Even loading it is slow actually. And I've got a nice picture of a toucan here, so I can load it, right? And I want to see if my model is able to predict it. So I'm loading the image in a NumPy array, and I'm generating a prediction. So let's see how good that model is doing. We need to use the decode prediction method, so that's just the prediction will return a label. So using the decode prediction method as provided by Keras, we can know like the actual class that was predicted. So if you do that, all right, so that's a pretty good model. Predicted 99.9999999 that image is a toucan. Pretty good. It's school bus as well. Really small probability though. So that's pretty good model. Good job. So now let's try to interpret that. So I'm just looking at the different labels because I'll need to pass the labels of the classes to Lime. But then I can load the Lime image explainer. I'm defining my explainer. So same thing as before when we were using Lime on tabular data. Here I will need to pass various arguments to my explain instance method. So I need to pass the actual image as a NumPy array. I need to pass my predict function. So you see here that it's much easier if we don't have fancy pre-processing to do, because you can just pass the predict method from your model. I just want to see the top two labels. That didn't matter earlier because we had a binary classification. Here we've got so many classes that we just want to see the two main classes that it predicted. Number of samples. Oh, actually I should load it now because it's going to be really slow. Number of samples. So that's the number of samples you want to sample from the distribution. So earlier I kept the default. Here I don't want to because it's fairly slow to generate images from scratch. So here I've only generated 100. So now we just import a few helper functions, and we're able to see what in the model it picked. And no. Okay. I need to import matplotlib. No, I did. Ah, perfect. Oh no, that's not great. Okay. Okay, I'm gonna be crazy and try 1,000. So the problem is that I did it earlier with 1,000 samples, and the explanation was actually pretty good. It was looking at the beak of the bird to predict what there's going to be a bird. So I thought it was a pretty good explanation. Now it's actually looking at the background. So that's not the right explanation that I wanted to show. Oh, by the way, there is a bit of that as well. Like, we are building a new machine learning model that we are interpreting. So you might like integrate your own bias in that model as well. So it's still not perfect, and that's why you need to discuss with other people and domain experts to know whether or not that interpretation is valid. Has it finished? Okay, no, it's gonna take a while. Is it faster in Colab? Have you guys run it in Colab already? Is it 1,000 samples?
One of the previous
It's not working.
There's missing dependency.
Oh, really? I don't know. Okay, let's just put back 100 because it's not gonna work. Please. Cool. Okay, so now we're gonna look at the explanation. Oh, great. Hey. Right, so that's what I was saying, it's unstable. It generated a new explanation now that is completely different than the explanation I had before, but this one I'm happy with, so I'm showing it. So here it's spotted that the fact that there is this beak here and this color on the bird explains why it decided it's going to be a toucan. And if I want to explain only with, so here that I chose 5 features, so an explanation with 5 features, so it's looking at 5 areas in the image that that it used to decide on what class it will be. If I just if I just decide give me one feature only that tells you it's a toucan, it's looking at this thing, which makes no sense at all, but fair enough. And a nice thing that you can do as well to debug. So I guess the takeaway here is that gotta use more samples than just 100. That's not enough to have an explanation that is stable. But what you can do as well is this. So you can see what is it saying? Okay. So you can see how different parts in the image positively or negatively affected the outcome. Oh, yeah, I'm looking at the bus. Okay. So I'm looking at, so class 779 is the prediction that it was a school bus. So here I'm saying like, well, take this prediction that it's a school bus and give me top 8 features, whether or not it affected that decision positively or negatively. So here it says that, well, that beak and that color really doesn't look much like a school bus, but those parts might do. And actually, if you would look into detail in that part in green here, there is a sort of like something that is a bit angular. So that, fair enough, but that's my interpretation here. So yeah, that's it for the image. Oops, I want to delete this one. For the image interpretation, and you can do same thing with text data as well. So that's really nice. If you're working with text data, I encourage you to look at the explainer from Lime, because it tells you. They have an example with emails, and it tells you in an email what made it classified as spam or not spam, and so it's actually highlighting the words. So it's quite nice to explain those decisions. Right, so I can just wrap it up. Yeah, so conclusion, if you're gonna use a complex model, you will at some point need to explain them, and there are 2 reasons for that. So the first one can be for ethical or regulatory reasons. Or the second one is to actually debug your model. So that's what we've seen earlier. Like if your model is not picking the right thing, it might be completely useless in the future when the data is a little bit different. So you can debug that. You can use it to debug. And also you can use it to communicate to others, and that's probably the most important one, that it empowers you to understand better your model and communicate to others how the decisions were made, and then they can give you feedback on what you need to change, what features you might not want to include in your model anymore, like we've seen here, the number of employees. Oh, and also in some regulations make it mandatory. So if you're in Europe, there is GDPR, so you need to be able to explain whatever prediction you're making. So it's not even your choice anymore if you want to deploy your model. Yeah, that's it. Thank you. Do we have time for some questions, or are we supposed to take questions?
We have like 4 or 5 minutes if
Okay.
people have questions.
Okay. Yeah.
I'll just send you the mic.
Great talk. Thanks very much. I was wondering where in your workflow usually doing model interpretations comes. Do you kind of wait until you have a model that you're happy with to do that sort of evaluation, and or is it every kind of iteration has some of that explanation piece?
Yeah, I think both. Like, so those are the two reasons I show here. There is, and even maybe a third one. So the first one is using it to debug your models to know if it's doing the right thing. So that needs to be done in your pipeline when you're trying to fit the best model. You need to know like if it's actually doing the right thing or not. Then the second one is once you're happy with the model, you need to communicate it. So you need to explain your decision. So that's second time when you need to do it. And then the third one is once you deploy it. So once your model is live somewhere there, you need to be able to like rewind and explain why that specific decision was made. So there would be like 3 stages where you need to do it. Yeah.
Kind of any kind of evaluating.
Yeah, pretty much. That's. I kind of see it as the same way when you're looking at the accuracy score or the classification report. That's the same thing, just a little bit longer. Other questions? No? Lunchtime then? Oh, yeah.
First, thanks for the talk and the demo. That was really good. I have a question about LAM. Can you go back to the page about LAM using the age to predict?
Which one?
Yeah, this one. So you are predicting age 20 and age 60, right?
Yep.
And as you can see, you are generating points
Yep.
in locally. And what if these two models have two different intercepts? It's likely. And how would you explain to people that, okay, you have different intercept, you have different baseline?
Right. That's part of your explanation. So like your model is valid only locally. So it was never meant to be globally to explain it globally. So here this model. And actually, the intercept, you don't even look at it much. You just want to know how that feature matters for your model locally. So here, what I'm expecting to do is this linear regression is not building the equivalent of my complex model. I just want to say, in this locality here, how important age is, or like other features. And by that, I look at the weight. So you're not trying to build a good model anyway. You just want to build something that is a good enough approximation locally that you can say, I trust it enough to know that the age here in this locality is important or not. So you wouldn't use it to explain your model globally. And that's a fair point with the intercept, but that would be the same for the different weights, right? Like, at age 20, the age might not be important at all, and then you would say that is not important feature, and then at age 60 it might become important, and then you would change completely your explanation and say, well, age is super important. It's a local model only.
I see, thanks. And do you have any suggestions on how to select the weights for the regression?
How to what, sorry?
Select the weights, basically the kernel size. I mean, how much weight you put on the distant points? I mean, how local it is.
To compute the similarity of the data you sampled. Those weights? Or which weight are you referring to?
So inside is doing a weighted regression.
Yep.
It's the weights on the regression.
So the weights are computed by Lime. I don't know exactly actually what's the algorithm. I don't know if you can override it, but they have their own way of computing. So it's somehow linked to the distance to the original point that you want to explain. I don't know exactly how they compute it from there. It's just linked to the distance, and they have a notion of similarity. Maybe you can override it and have your own definition of similarity there. Yeah.
Oh, thanks.
Thank you.
Thanks for the talk. So my question is about kind of when you do the visualization of the model using Lime,
Yep.
and basically it's just using linear model to approximate it. So I feel like I'm worried that, like I tell my boss that, I have this black box model that kind of works out well, and he's concerned. I'm like, oh wait, but I have this amazing tool that can visualize anything. But then when I run it, but okay, it doesn't actually do a good job kind of approximating the model. And shit, okay, what do I do? Like, is there anything that can tell me, that can explain why is it not doing this kind of approximation as good, or how can I improve that?
Well, so the thing is that your model, if you're gonna use complex models, so by kind of like for example, if you're using an ensemble model or whatever, it's not gonna be linear by definition. So when you're trying to fit a linear regression there, it's never gonna be a perfect fit anyway. So that's you can see how good it was with the R squared, or like debugging a little bit exactly what your linear approximation is, but it will never be. So ideally, the perfect explanation would be if we have a perfect fit locally. That's not going to happen. So you need always to keep that in mind. But it's hard to have like an answer to that works every time. I guess and that's probably one of the issues as well with those methods, is that you're building a new model that is simpler, and then you're interpreting that yourself. So there is a lot of bias going on there. So yeah, so I don't really have an answer to this question. I wish I knew, but you're building a new model that is an approximation that isn't perfect, and you're trying to use that as a proxy to understand the impact of your features. That's all you're doing, and then yeah, you can say whether or not that makes sense, and you can also check whether or not that approximation is good. That's all you can do pretty much. I'm not sure I answered your question.
No, yeah, that's fair enough. Thanks, that makes sense.
He walks over here.
Okay. Yeah.
Last question. I was just wondering if there's like maybe this is just a question about the paper, but are there bounds on like the confidence of these linear approximations to your model? Is it easy to bound it so that you could at least say like, oh, this approximates with the original model with this confidence? I know that we have R squared to say how well it's doing in that region, but in terms of like relating it to the original model.
You mean globally?
Even on local patches.
Yeah, because that model should really be taken only locally, first thing.
Right.
It has no sense at all globally. But then, yeah, locally you can only see how well the how good an approximation your linear regression is.
Yeah.
So there isn't much more that you can do than that. You can run it several times. Actually, that would be a good idea, because you're still sampling.
Yes.
There is the instability due to the random sampling. So it's really not a perfect technique.
There should be some way to bound the error, though, like in relation to the original model. Anyway, I'll look at the paper.
Yeah.
Okay, but my actual question is, Stan, what was the last visualization you showed? I forget the name.
SHAP.
SHAP. Yeah. So can you talk about the units on the
on this axis.
Yes, and also, yeah, go ahead.
So those are the SHAP values, so that they don't, I think, they unit less.
Okay, so these are some combinatorial.
Yeah, it's just so
statistics.
that's what I was explaining really quickly right here. So we are just like trying to measure the impact of adding each feature to all the subsets of features that don't have this, and then we aggregate that somehow, and that's how we get this this value, whether it positively or negatively affects it. So you get this this Shapley value that you can compare from a feature to another.
Okay.
But by itself, I don't think you can tell much with the value. You can only compare it with the rest, if that makes sense. So when you have it here, here the minus 2.1 itself doesn't tell you much, but then you can compare by how much of an impact so that's just a measure of impact. So the number of employees here seems to be to have a larger amplitude in making in pushing it to the negative side, whereas this feature here has a different amplitude. So it's used to compare the importance of the different features, but by itself doesn't have much meaning.
Okay.
We're gonna have to break for lunch. All right, it's time for lunch now. Thank you.
Okay.